everyone, welcome to lecture 11 of AREC 333. Today we will continue with technical aspects of production two-input case. We will finish this topic today, and next lecture we will move on to profit maximization of two inputs. The outline for today is here. The main focus will be homogeneous production functions. And before that, I actually would like to cover a little bit of the marginal rate of technical substitution that we didn't finish last lecture. And for the homogeneous function, I actually want to introduce to you guys a very famous production function, which is Cobb-Douglas function. We will not cover the profit maximization section that I listed here. This is to give you a heads up for what's coming in next lecture. The readings highlighted in blue here are for profit maximization that we will cover for next lecture. So if you're interested after today's lecture, you can read those sections. Last lecture, when we mentioned that isoquant should be both negatively sloped and convex to origin to exhibit the diminishing marginal rate of technical substitution property. And I actually want to explain a little bit more of what could it be if the isoquant is not convex to origin. For example, if it's concave to the origin, which is a shape here, then if that's the shape, we will not have diminishing MRTS. So for example, suppose we're starting from here and we want to increase the yields of X1, and you can see from here to this point, the X1 yields increase by 1, and this is a decrease in X2. If we move further to the right, and we can find that for the next increase in X1, the yields, the substituted X2 actually get increased. And if we move further to the right, and we increase 1 unit of X1, and we can reduce the use of X2 for even more. So what we're having here, instead of having a diminishing marginal rate of technical substitution, we're having an increasing rate of technical substitution. So the more X1 you use, the more X2 can be substituted, and that is violating the law of diminishing returns. I have shown you that the patterns of isoquants can tell you the whether you're having a constant decreasing or increasing returns to scale. And we can also tell more from the patterns of the isoquant curves. So for example, we can tell how well one input is substituting the other inputs. And here we have 3 typical isoquant patterns, and that is actually showing you the substitutability of the 2 inputs. So for this pattern, we say that there's imperfect factor substitutability. So that means that one input can substitute the other, however, not perfectly. And usually, all of the input cases that we are interested are having this pattern. We also have another pattern is that you cannot replace one factor by the other. The 2 factors has always need to be used proportionally. Then we have this pattern. So for example, if you're producing here, it's having the same output as if you're producing there. So the increase in X1 is not adding anything to your output. Case here, example here is a tractor and the driver. So 1 tractor, 1 driver. If you have 2 tractor, 1 driver, you're still ended up with the same output. And the last case is when one factor is able to perfectly substitute the other factor. So here, case will be, for example, a fertilizer is sold in small bags, or if you buy a big bag of your fertilizer, those two will have exactly the same impact on your output. It turns out that RTS is also linked to the MPP concept. So this is why I mentioned at the very beginning of the course that MPP is going to be super important for this course. And let me actually show you why that's the case. So again, we will need the total differential equation. So total differential equation here, we have seen this. And then the important assumption here is that we are moving along an isopoint curve. So if we're moving along the isopoint curve, that means your y is fixed. And if your y is constant is fixed, then that means your change in y is 0. So if you, as long as you are staying in this isopoint curve, you're not jumping between different isopoint curves, then dy equal to 0. So dy here, this term on the left will equal to 0. Then if this is equal to 0, we can actually write here 0 equals to MPP1 dx1 plus MPP2 dx2. And if we put this to the left side, then we can write this as the negative of that term. And we further rearrange the terms to put this one on the right. And then we can put this MPP2 to the left. And we ended up with this relationship. And if you do remember, this part is the definition of RTS. So this is the definition. So then you get this RTS is actually the ratio of the two MPPs. So the rate of technical substitution is equal to the ratio of the marginal physical product of those two inputs. We can also introduce another elasticity concept, and you can probably tell from the screen that that term is pretty complicated. So what I'm trying to show you here is that we can define a elasticity of factor substitution, and actually there's some history in the field of production economics about which elasticity of factor substitution we should use. But this is ended up with the one that's used most often. But I do not want to go to the math here, and I don't think that's a focus of this course. And what we should be aware, or what we should understand, is that the larger the elasticity, the greater the degree of substitution between those two inputs. So use the example that we have used before for the three different isoquant patterns. The first one, when the two factors cannot perfectly substitute each other, then this one is between 0 and infinity. When the two factors has to be used in fixed proportion, then there's no substitution between those two inputs, and the elasticity of substitution is equal to 0. And finally, if the two factors or the two inputs are perfectly substitutes, then the elasticity of substitution is equal to infinity. Okay, let's move on to homogeneous production functions. And the first question you might have is, why should we even care about homogeneous functions? So the short answer is that homogeneous functions, they have special level curves, special return to scale, and special rate of technical substitution. And I will explain to you why in a little bit. But basically, if we have a homogeneous functions, our life will be much easier. You could probably escape a lot of the math and calculations later on when you're doing the profit maximization. And actually, a lot of the functions that we have met in economics are homogeneous functions. It's just we never mentioned this name before. And there's only actually one exception here for, at least for this course, the functions that we have met that's not homogeneous functions is when we have quadratic production functions. I will explain in a little bit why that's the case. But keep in your mind that we will actually prefer our functions to be homogeneous functions. So what is the definition of homogeneous functions? Let me actually give you the mathematical definition first. Then I will explain to you how do you translate that into verbal words. So a production function, or you may say any other function, since in this course our focus is production function, I will just say it's production function, but it can be applied to other functions as well. Production function is homogeneous of degree k if the production function can be written as this special case. So what does this mean is that for a production function, if we increase our input yields by t, so both x1 and xt are scaled by t times. For example, if t equals to 2, that means both x1 and x2 will be doubled. And if you double your input yields, or all of your input yields, then what's going to happen to your output? So this is your original output when you didn't change your input yields. However, if you increase your x1 and the x2 both by t times, then the output is actually this much. So there's a very special case is when k equals 1, and we are having a constant return to scale. And why is that? So basically, when k is equal to 1, this function is saying that if you increase your x1 and x2 yields to tx1 and tx2, then your output is gonna be increased by t times as well. So if you double your x1 and x2 yields, your output will be doubled. So that's basically the case for a constant return to scale. And if, however, the output is not t times the original output level, it becomes t to the k, whether you're getting more output or less output, then that depends on the value of k. So this homogeneous function is trying to give you an idea of what if you change your scale of production, then what's going to happen to your output. Let me give you several examples here so you have a better understanding of what is homogeneous function and what is the degree. So this function we have seen, this is the cost function, and R is the price of input 1, and R2 is the price of input 2. So this is the cost from the input side. And this function is HOD1. So HOD means homogeneous of degree 1. And why is that? Is because if we increase our, if we change our x1 to t times x1, then what's going to happen is that our new cost will become this much, and this is actually t times r1 x1 plus r2 x2, and this is t times the original cost. So here we can say that we don't have a exponential component here. However, that is because that's 1. When it's 1, we can just skate right in that 1 there. So this is homogeneous of degree 1 function, And this function is actually the Cobb-Douglas function that I'm gonna introduce to you in more detail later on. However, here the degree is homogeneous of degree beta 1 plus beta 2. And let me do this one more time, deriving what is the degree of homogeneity. Then for the next two, I will leave that to you for a practice. So here, let's write this in more detail. If we change our input use from x1, x2 to t times x1 and t times x2, then the resulting output will be tx1 here to beta 1 and tx2 here to beta 2. And for exponential functions, we can simplify this expression separating the t and x1. So we have this property here, and here you can recognize that there's a common term t here, so you can actually further simplify this equation to t beta 1 plus beta 2, and then after that we have ax1 beta 1 x2 beta 2, and this term is actually your y for x1 and x2. So let me write this down so that it's more clear how you can tell the degree. So we are actually here having y tx1 plus tx2 is equal to t beta 1 plus beta 2. And then we have our original function here, where the inputs are just x1 and x2. So for this case, we can see here the exponential term is beta 1 plus beta 2. If you compare this equation with our definition here, and you can notice that the k is exactly this beta 1 plus beta 2 here. So this function is having homogeneous, this production function is homogeneous of degree beta 1 plus beta 2. And for this function, the third function, that's a special case of the fourth function here. So the last function here is what we will call it quadratic production function, because the highest term here is 2, so this is a 2. This is a quadratic production function. The quadratic production function is not a homogeneous function in general. However, if we have this special case here, so this for the fourth function to become the third function here, we have to have a1 equal to 0, a2 equal to 0. And then if we have these two assumptions here, then our function is homogeneous of degree 2. So the third function here is homogeneous of degree 2. You should try to derive this or try to find out this degree here by yourself. And these are actually the answers that I provided to you guys. So the last one is not homogeneous. And as I mentioned to you guys, that homogeneous functions have nice properties. And there are actually 3 nice properties that I want to explain to you, but let's focus on the first one. So the first one is about the isoquants. What's so special about the isoquants of homogeneous function is actually, I have a graph here, which are the isoquants, and I have x1 and x2 on the axis. So you can notice there are 3 lines here. So last lecture we mentioned that along each of those lines, the input use will be in proportionate well, the input will be used proportionately. So let me actually explain to you the first property here about the isoquant of homogeneous functions is that the isoquants are just the radical expansions or contractions of each other. What does that mean is that if we pick, for example, several points on one isoquant curve, let's focus on this one. Let's say this is y0. The upper level is equal to y0. Then we pick 3 points, and let's actually first look at a0. So at this point, if we increase the input use by t times, and so assume here is a1, then here is a 0. This is x1, a0, x1, a1, and we say that x1, a1 is equal to x1, a0 times t. Then we also have the same relationship again, x2, a1 equals t times x2, a0. So if that's the case, then the input use increased by t times, and the output use will be increased by t to the k times. So at this level, this isoquant where a1 is located, then your y, suppose this is y0, then this will be t to the k times y0. So that's the upper level for that point. And if you pick another point here on the y0 isoquant, then if you also increase the input use at b0 by t times, and you get to the point b1, then at b1, your output level is still t times k, t to the k, and multiplied by y0. And if you pick another point, C0, and increase the input use by t times, then you get to C1. Again, the output level is still tk times y0. So this second isoquant curve, let's call it y1, is equal to tk0. So if you pick any point on the isoquant y0, and if you scale that by t, then you ended up at y1 equals to t to the k times y0. So that's saying that y1 is just a radical expansion of y0. And if you want to go the other way, you start with y1, and if you want to go to y0, then your input use becomes 1 over t times of your input use, and that is a contraction of y1. So this is the first property of homogeneous functions is isoquants are nice. And the second property here is that they return to scale. This is about the return to scale of homogeneous functions. So here, the ES is the elasticity of scale. And from last lecture, we learned that this ES is equal to the sum of the two partial elasticities of production, or you can also call E1 and E2 the factor elasticity. So the total elasticity of production is ES. The two partial elasticities are E1 and E2. ES equals to E1 and E2. And if you have a homogeneous function, then your life are much easier, is because then your elasticity of scale will just equal to K. And that's a really nice property. Remember in the nitrogen and potash example, I asked you to calculate E1 and E2, and you have to go through several steps. However, this time, if we are not having the quadratic production function, we're having other functions of those types that I have given you example, those homogeneous functions, then you don't even need to calculate. You can tell from the production function that the elasticity of scale is K. And from this K, you can further tell the return to scale. If K is equal to 1, then we're having constant return to scale. If K is smaller than 1, we're having decreasing return to scale. And if K is greater than 1, then we're having increasing return to scale. How did we get to this point where the elasticity of scale is just equal to K, which is the degree of homogeneity? I will derive the math here. However, I want to let you know this is not required by this course. This is only for those who's interested in the math derivation here. For those who are not interested, you can just skip the rest of the math derivation and go to jump to the point where I started the next slide. The second nice property about homogeneous functions is that its RTS, rate of technical substitution, is constant along those rays start from 0, or you say those ray lines. So in this graph here, for example, I have one ray line here, another ray line there. What do I mean RTS is constant is that, for example, if you pick one point here, then you find out the slope of the tangent line at that point of the slope. And then if you find this point where the 2 points are in the same ray line, in this ray line, and then the slope at this point, the slope of the isoquant at that point is the same as the slope at this point, and also the same as this point. So the RTS is the same if your input use change is along a ray line. So along a ray line, your input use are in fixed ratio. So why is that? It's actually related to what I have just showed you before. But first, let's write what is RTS, right? RTS is the slope of the isoquant, and if it's a slope of something, then it's measuring the rate of change. So that is dx2 over dx1. And if you're having a hard time remembering what is RTS 1, 2, then it is actually easier to just remember x1 is written in the horizontal axis and x2 is written in the vertical axis. And then if you pick a point and the slope of the tangent line is the change in x2, and on the horizontal side is change in x1. And if we want to find out the derivative at that point, then we use d instead of that delta triangle there. So this is dx2 over dx1. And again, remember, because this is downward sloping, so the slope is negative, we put a negative sign in front here to make sure this number is positive. So this is the definition of RTS, and we showed in last lecture. It's nice that this RTS is just the ratio of the partial derivatives, which are also the marginal physical product of those two inputs. So, but you have to pay attention that here is dx1 over dx2 over dx1. Well, when it's expressed as a ratio of MPPs, it's 1 on top and 2 on the bottom. So that's RTS. And why is this related to the constant RTS along ray lines? It's because here, again, this is the first point, and let's say this is MPP1. At that point, we have MPP1, or let me write it in more detail, X1, MPP X2. And then at this point, suppose the input yields, they're still in fixed ratio, but now it becomes Tx1 and Tx2. So if that's the case, I have actually shown you through that math, and if you don't want to go through that math, that's okay. But you just need to trust me that this is true, is that the ratio of MTP is equal to the ratio of MPP when your input yield is increased by T times. So the reason that those two MPP ratios are the same, then if you translate that to this graph, that means the RTS is constant along the ray line. So that is another nice property of homogeneous functions. Later on, this constant RTS will have implications for cost minimization. Let's have a quick summary of the three nice properties of homogeneous functions. Again, so I do apologize for the math there, and I want to emphasize again, those are not required for this course. It's only for those of you who are interested. And however, you do need to know these three properties listed here about homogeneous functions. First is that the isoquants, they are just radical expansions and contractions of each other. Second one is about returns to scale. So K, which is the degree of homogeneity of your production function, is actually the same as the elasticity of scale. And if K is equal to 1, you have constant return to scale. If K is smaller than 1, decrease in return to scale, and K greater than 1, increase in return to scale. So this is really convenient once you have a nice production function. You don't need to go through all the math. And the third property is that the rate of technical substitution is constant along ray lines from 0. Finally, we get to the most famous production function that's used in both and out of agriculture. That is the Cobb-Douglas function. So I feel like if you're studying production economics, then you'll have to know this Cobb-Douglas function. So it is first used in 1928, and I actually have the reference at the bottom here. That's a journal article published by Cobb and Douglas, two person, and it's actually here, the journal is AER, it's one of the top 5 journals in the economics field. So in their original paper, there's only 2 inputs here. One input is K, the other input is L. K is for capital and L is for labor. And this is the original Cobb-Douglas function that they used here. You have to pay attention here that the 2 exponential terms are alpha and 1 minus alpha. And if you do like spend a little bit time here, you will figure out, or maybe it's very obvious, that our alpha plus 1 minus alpha is equal to 1. And from what we have just learned, that Cobb-Douglas function is homogeneous of degree alpha plus 1 minus alpha, and that is equal to 1. So this is the elasticity of scale for Cobb-Douglas function. And what can we tell from that? It's constant return to scale. So once your production function is written this way, then you're having a constant return to scale production function. And what does that mean is that if your capital and your labor are increased proportionally, then or if you want it to be more specific, if they are both doubled, then your output will be doubled as well. So that's really a nice property of Cobb-Douglas function. Later on, when Cobb-Douglas function was published in the journal, there were some generalizations of the function. However, this production function, before I go there, there's actually several other properties of Cobb-Douglas function that I want to emphasize here. First is that this production function is showing both diminishing marginal return of K and L. And as we mentioned before, this diminishing marginal return is important for the economic implications. And what we also should pay attention here is that this production function is not an adequate representation of the three-stage production function. So Cobb-Douglas function doesn't have all those three stages. And we just mentioned it's HOD1 or constant return to scale. And the last point is that at the time, in 1928, this very simplified production function is easy to estimate with the tools of the day. So imagine at that time there's no computer, and if you do have a lot of data and you want to estimate the parameters alpha here and A, so those are the two parameters, then you have to use some simplified forms so that you can actually make sure the calculation can be done. Of course, today we can use more complicated function forms, and those production functions might have some better properties than Cobb-Douglas function. And actually, in one of the lab sessions, I'm actually gonna show you guys how to estimate a Cobb-Douglas function. And we will actually use Excel, and then I will provide data, and then we can actually practice how can we estimate the function. Then from the parameters we estimated, what information can we get? How can we what information can we get from that estimation? So the original Cobb-Douglas function, as we have shown, has a property so that the return to the elasticity of scale is equal to 1, and that means constant return to scale. However, later on, economists realized that a lot of the case we don't want to restrict that the return to scale is constant. So there's some generalization of the Cobb-Douglas function. First is that you can notice here there's more inputs. So instead of only have 2 inputs, we now allow n inputs here. And another property here is that the exponential terms here, there's no restriction that the summation of those exponential terms equal to 1. And for that, actually, we are not restricting the production function to be constant return to scale anymore. The elasticity of scale is equal to those summations. And even nicer about the Cobb-Douglas function is that here, beta 1 is just the factor elasticity of x1. And if you still remember how you get, this is the E1, if you go back to your nitrogen and potash example, you have to go through a bunch of steps to get that E1. Here, once I tell you we're having a Cobb-Douglas function, you don't need to do any of the calculations. You can directly tell that beta 1 is the factor elasticity, and the return to scale is equal to that summation. And if this summation is greater than 1, then you're having increasing return to scale. Cobb-Douglas function have all the nice properties we mentioned about homogeneous functions. And I actually want to show you here what a Cobb-Douglas function of 2 inputs look like and what is its isoquant. So on the left is the production surface, and this one is actually a very special Cobb-Douglas function, is where y is equal to x1 to the power of 0.5 and x2 is also 0.5. So immediately you will be able to tell that 0.5 plus 0.5 equal to 1. So the elasticity of scale is equal to 1, and we are having a constant return to scale. So for the isoquant if we're having CRS. Then if we are moving along a line, a ray line, then the distance between those different isoquant curves should be the same. So this is a symmetric Cobb-Douglas function. However, a Cobb-Douglas function needn't to be that way. Here we have an example of x1, the power of x1 and x2 are different. And you can see actually from both the production surface and also from the isoquants that there's that asymmetry there. So Cobb-Douglas function, I will introduce this much for now, but later on when we are in the production maximization topic, then we will use the Cobb-Douglas function example again. And I'm hoping that you will realize that if you have a Cobb-Douglas function or a little bit more general, a homogeneous function, then those profit maximization problems will become easier.
We have a little bit time left. Let me give you a summary of what's covered under the technical aspect of two inputs. And this is the content of lecture 9, 10, and today's lecture 11. So when we have more than one variable input, our production function will be written differently. So before we only have one variable production function, then the x2 until xn are all fixed. Then we can, for notational convenience, we can just write y equal to fx. Now we have two inputs, or it can be extended to more than two, but let's just use two as an example. Then our production function can be written this way, x1 and x2. Here are variable inputs, and again, for notation convenience, we can write it this way. And the difference between one variable production function and two variable production function is that for the one variable production function, we have a curve. So we can use 2D graph to plot the production function. However, when we have the two variable input production function, then we use 3D graph to plot the production function. And I showed you in class what the production surface look like. So now with two or more inputs, we use surface to describe. We are not having a production function anymore. However, a very important point here is that since we have two inputs, if we want to study the properties of the production function, then it's a good start to holding one input constant and then study how does our output change with the other inputs. And we started the technical aspect with, again, the APP and MPP concepts. And for the one input case, we just write APP. However, for the two input case, we have to indicate which input we're talking about. So APP is the average productivity of x1. So this is y1 over x1. And we should always keep in mind that this is keeping x2 constant. And it's same for APP2, is just y equal to y over x2. And for MPP is we actually introduced a new concept, partial derivatives, to calculate MPP1, because in the multiple input production function case, we are not having dy over dx anymore. So this is for one input case. If we have two inputs, then we need to use partial derivative of y with respect to x1. So this is the rate of change of output due to the change in the input x1 while holding x2 constant. And we did explain that if we're holding x2 constant, then we can convert a 3D graph to a 2D graph, and once we hold x2 constant, then our production function becomes a curve again. And those are the APP and MPP concepts. And also with the APP and MPP concepts, we introduce the factor elasticity. So E1 is MPP1 over APP1. That's the factor elasticity. And with the second input, it's also the same. Those two are factor elasticities, or we may call it partial elasticities of production. And later on, we said that there's a elasticity of scale is equal to the summation of those two partial elasticities of production. So this one is elasticity of scale, can be thought of as the total elasticities of production. Those two are partial elasticities of production. Sometimes we call it factor elasticity. And that's for the APP, MPP concepts. And then we started with a new concept for the two input case is called isoquants. And we need the isoquant concept is because, again, for the two input case, we need a 3D graph, and 3D graph sometimes can be difficult to work with. The isoquant can help us, again, convert a 3D graph to 2D graph. And for isoquant, for the two axes, we have the inputs, not x and y. So both axes are inputs. And we say that one isoquant represents a particular output level. You can say just y equal to 5 or something. So along that isoquant curve, there's infinitely many different combinations of x1 and x2 to produce the same level of output. And we can go to our production surface and trace out different isoquant curves. So this is basically projecting the level curves where you're having the same outputs, and then project that onto the x1 and the x2 plane or space. So this is what our isoquant curves look like. And then to indicate for the two input case, a little bit different than the one input case is there are so many different combinations, and to later on figure out which combination is the best for the producer. Either the producer wants to minimize costs or maximize profit, then the producer has to decide which point along the isoquant curve to produce. And to figure that out, we need to introduce a new concept, which is a rate of technical substitution, or sometimes it's marginal rate of technical substitution. RTS is defined as the negative of the slope of the isoquant curve, and that is linked to the MPP concept. It can be written as a ratio of those two MPPs, and it measures the rate at which the one input can be substituted by the other input. And we did also introduce the concept of the elasticity of substitution, but here I'm not asking you to derive it or calculate it mathematically. However, you do need to understand what elasticity equal to 0 or infinite mean. So if elasticity equal to 0, that means there's no substitution between the two inputs, and the isoquant curves having the L shape. And if there's perfect substitution between those two inputs, then we're having the linear isoquant curves. And what we are interested in the most is the case where the isoquants having this shape, and this is where the two inputs can imperfectly substitute each other. We also mentioned that the isoquant curve patterns can also tell us about the returns to scale, whether it's constant return to scale, decreasing return to scale, or increasing return to scale. And then we also, in this lecture, we also introduced homogeneous functions, and we mentioned that there's nice properties of homogeneous functions. So basically, there are three properties of homogeneous function. First one is about the isoquant, and the second one is about the elasticity of scale, and finally it's the RTS. So if you're having a homogeneous function, then your isoquants are expansions or contractions of each other, and your elasticity of scale is just k, which is the degree of homogeneity of your production function, and your RTS is constant along the ray lines from 0. And we also introduced a very special type of homogeneous functions, which is Cobb-Douglas function. And Cobb-Douglas function, which is the most famous production function of all, and it has all three properties of the homogeneous functions. And what's more, it's that you can actually tell from the parameters of the function here, x1, x2, beta 1, beta 2. So the beta 1 here will be factor elasticity, and beta 1 plus beta 2 is the return to scale. So it's a really nice production function, and later on we will also spend time on this function for profit maximization problems. So those are the technical aspects of two inputs, and next lecture we will move on to profit maximization from input perspective for two inputs.